The vast expanse of the sky has always beckoned humanity with its promise of adventure, exploration, and conquest. Since the Wright brothers made their historic first flight over 100 years ago, aviation has come a long way. Today, sleek, powerful planes crisscross the skies, connecting distant cities and carrying countless passengers to their destinations. But amidst this incredible progress, there's one thing that has remained constant: the design of the airplane wing. It's been the same for decades. But what if we challenged convention and dared to dream bigger, bolder? What if we explore a radical concept that could revolutionize aviation as we know it? Brace yourself for the unconventional, the extraordinary, and the thought-provoking. Welcome to our channel, where we dare to challenge the boundaries of imagination and explore the limitless possibilities of science and technology. Today, we delve into a realm where innovation knows no bounds. Throughout more than a century of aviation development, humans have continuously experimented and improved every aspect of the aircraft. From the engine, the shape of the fuselage, the cockpit, to the wing, the most iconic and important part. The wing plays a key role in creating lift and determining the aerodynamic performance of the entire aircraft. However, sometimes a bold idea can break all the standards. That is, the oblique wing. This idea sounds crazy. An aircraft with an asymmetrical, offset wing, in which one wingtip extends forward and the other tip is pushed back. Seen from above, it looks like a twisted arrow, making anyone who sees this design for the first time surprised, even skeptical. Can such an unconventional design work? Let's begin the journey to discover this idea that can change the aviation industry forever. The origin of the crosswing. With a crosswing, a design that seems to defy all intuitive sense, the first question is, why? Why deliberately make something unbalanced with a wingtip on each side of the aircraft pointing in different directions? Why not have a single wing in the middle, symmetrical, like all other aircraft? The answer, like any breakthrough, lies in pushing the limits of the known to unlock untapped potential. When an aircraft flies at subsonic speeds, air resistance increases with speed, but still within manageable limits. However, once it exceeds the speed of sound, the aircraft faces a huge problem: wave drag. This is the type of drag that is created when the aircraft creates shock waves in the air, something that makes maintaining high speeds, consume huge amounts of fuel, and causes a lot of aerodynamic instability. Throughout the 20th century, engineers have been trying to find ways to reduce this drag. One successful solution was the swept wing, as seen on many fighter jets and high-speed commercial aircraft. By sweeping the wings, the aircraft can trick the airflow, reducing the effective angle of attack and delaying the onset of shock waves. But sweeping wings were only the beginning. Some scientists wondered, if we could make the wings flexible and able to rotate depending on flight conditions, performance could be further optimized. And so, the idea of the oblique wing was born. Instead of having two symmetrical wings, the oblique wing is a single wing that rotates around a central axis. At low speeds, the wing is horizontal like a normal aircraft, creating maximum lift. But as the aircraft accelerates, the entire wing tilts, like a giant fan turned at an angle to reduce drag. The advantages of this design are: naturally reduces supersonic drag, because the entire wing is tilted into the airstream. The aircraft can travel at very high speeds without encountering the large drag of conventional designs. No need for complex double-wing structures. Single-wing structures reduce weight and mechanical complexity, making them ideal for long-range high-speed aircraft. Adapts to each phase of flight. At low speeds, the wing returns to a horizontal position to optimize lift. At high cruise speeds, it rotates to optimize performance. Sounds appealing, right? But the theory is only part of the story. There are still many unanswered questions about how an aircraft like this can maintain stability, balance its center of gravity, and operate in practice. NASA and the AD-1, not just a theory. The diagonal wing was tested by NASA in the 1970s through a prototype called the AD-1. The AD-1 was a small aircraft, looking like a strange glider, the long wing that could rotate from 0 to 60 degrees. When the AD-1 flew, it seemed to be leaning to one side, making observers curious. Why doesn't it fall off immediately? The results showed that at low speeds, the AD-1 could fly quite stably, even with the wing rotated completely out of the way. However, the limitations of the structure, materials, and controls at that time prevented the project from going further, however. This experiment was the clearest demonstration of the potential of the diagonal wing, a design that seemed crazy but was completely feasible. Despite the success of the AD-1, the aviation world has yet to see a commercial or military aircraft using a diagonal wing in actual operation. So what prevented this idea from becoming a reality? The answer lies in many factors. The technological limitations of the time, the cost, the complexity of the controls, and of course, the fear of change in the aviation industry, which always values stability and safety. What makes a wing so good in aviation? The key word is probably efficiency. Every liter of fuel saved, every kilogram of weight saved, every percent of drag eliminated, all contribute to a faster, lighter, farther flying, and more cost-effective aircraft. That's why the wing design, as strange as it may seem, has captured the attention of the aviation world for decades. It promises a leap in performance that traditional designs have had difficulty matching. As mentioned earlier, when an aircraft travels above the speed of sound, the drag generated by shockwaves increases exponentially. To combat this, engineers have used many tricks such as pointed noses, swept wings, elongated fuselages, etc. However, the wing offers a revolutionary solution. When the wing is angled, the entire wing plane becomes almost parallel to the airflow. This significantly reduces the drag created by the leading edges, while also reducing the area of the wing exposed to the air unnecessarily. Instead of having a fixed wing with a large angle of inclination, as on fighter jets, the diagonal wing can shape as needed depending on the speed. The result? Less fuel, less drag, and higher speeds. This is especially ideal for aircraft flying at speeds of Mach 1.2 to Mach 2, where aerodynamic efficiency is crucial. One of the most attractive features of the diagonal wing is its ability to change shape depending on the flight conditions. At low speeds, such as when taking off or landing, the aircraft needs maximum lift and high stability. In this case, the wing can be horizontal as in a traditional design, providing maximum area for the airflow to pass through and creating strong lift. As the wing approaches cruising altitude and speed, where drag becomes a major factor, gradually tilts to transition into an aerodynamically optimized mode. This transition can be controlled automatically or via an onboard computer, depending on the design. You might think that designing a swept wing would be much more complicated, and it does require sophisticated technology to control it. But oblique wing aircraft are mechanically simpler than traditional variable sweep wing aircraft. Instead of having two independent symmetrical wings, a swept wing aircraft has just one wing, rotating around a central axis. This reduces the number of moving parts, overall mass, and maintenance costs. Results from NASA tests show that the swept wing not only works, but can also maintain good stability at both low and high speeds. Although flying an aircraft with a swept wing requires a precise control system, modern automatic flight algorithms are fully capable of handling this. Computer simulations show that swept wing aircraft have higher lift-drag ratio, better fuel efficiency at high cruise speeds, superior acceleration, and altitude stability. This opens up great potential not only for military aircraft, but also for commercial air transport, especially for future transcontinental or high-speed routes. Why hasn't the wing taken off yet? Although the idea of a wing design offers many advantages in theory, in testing to date, we have yet to see such an aircraft produced and operated on a commercial or military scale. The question is, why has a design that is highly regarded in theory and testing not yet flown in the real world? The answer lies in a complex combination of technological, economic, engineering, and even psychological factors.